Hello, my name is Professor Lajimi. I'm going to continue teaching multivariable control system, the introduction to an introduction to multivariable control systems. Sometimes I apologize because I have to abruptly cut off the video because I have to do something. And then sometimes I really get tired at the end of each video, and I apologize for that. If I make any mistake, you can essentially let me know. Just to, and as you see some emails here, bottom of um, your screen essentially, and so all right. I'm just trying to make sure that. Oh, let me just. I think sometimes you can't really see the bottom of my video. All right, so let me start here. So this is an introduction to multivariable control. My name is Professor Lajimi. I'm a member of a triple E and a member of Institute of Physics. I have a PhD in Systems Design Engineering from University of Waterloo, and then I had a master's degree before that. I've got my master's degree from École Polytechnique Fédérale de Lausanne in Switzerland. And these are the email addresses you can talk to me, you can contact me. All right, let's go to page 100. I'm not sure, I've already talked about these. Yeah, I'm here. All right, now I'm gonna go to the full screen. I have to fix this screen thing somehow later. All right, so let me just give me a second. So the singular value decomposition is, as just to recap, we are looking for the worst case scenario and then the largest amplification and the least amplification. So obviously the output to input is going to be between these two values, between maximum and minimum. So the singular value decomposition, as we said before, applies directly to non-square plants, and that's the advantage over, like, one of the advantages over eigenvalue method. And this is one of the biggest reasons we prefer SVD over eigenvalues. In real systems, it is extremely common to have more sensors than actuators. So it's oversensed. And more actuators than outputs, redundant actuators. So in real system, it makes sense. In fact, it completely makes sense to have more sensors than actuators, in more actuators than outputs. What's the result of that? What's the result of having more sensors and then actuators and more actuators than outputs? What happens is that our plant matrix, our plant is not anymore a square plant, right? Because we have more sensors than actuators, and then we have more actuators than outputs. So the system matrix, it needs to somehow adjust for that, adjust to take us from right-hand side to left-hand sides in our state space systems. Then we have to, we're gonna have a non-square plant. Unlike eigenvalues, this VD is defined for any L by M matrix. So for SVD, unlike eigenvalues, we don't need to have L by L or M by M matrix. It can be L by M, a non-square matrix. And this directly ties into mechanical systems. We have more accelerometers, few actuators, and we have many thrusters, few controlled variables. All right? This is reality. We're gonna talk about our real systems, and it's always the case. So as we just said, we have more outputs than inputs. At most, M singular values are non-zero. At most, M singular values are non-zero. This M singular value at most, which is non-zero, if you recall, it relates output to input. But then obviously, because M is the lower number here, at most M singular values are non-zero. So again, this is the result of our assumptions, and it's crystal clear why we are saying at most M singular values are non-zero. The remaining output directions cannot be influenced by the inputs. So we had this M here, and because of what we had here, we talked about this y at most M singular values are non-zeros. And then the remaining output directions, we had L minus M is the difference between the number of inputs and number of outputs. So the remaining output directions cannot be influenced by inputs. And that's, again, that makes sense. That's logical. The remaining output direction cannot be influenced by inputs. Input space is m-dimensional. Think about it in geometry terms. Input space is m-dimensional. So you can only span an m-dimensional subspace of the output space. And what does it mean practically? It means that some measured motions are fundamentally uncontrollable. We had lower number of inputs, so some measured motions are fundamentally uncontrollable. And sensors may measure motions that no combination of actuators can generate. Think about this example. Consider a flexible structure. You might measure 6 strain gauges. These are the outputs, but only have 2 piezo actuators, inputs. Some strain patterns will never be produced / controlled by those actuators. So again, you might measure 6 strain gauges, you might use 6 strain gauges to measure outputs, but only have 2 piezo actuators as inputs on your flexible structures. What happens is some strain patterns will never be produced controlled by those actuators. More inputs are now. That was case 1. Now case 2, we have more inputs than outputs. Case A, we had less inputs than outputs. Now we have more inputs than outputs. So again, at most, L singular values are non-zero. Again, between M and L, the lower number determines what's the maximum number of singular values which are non-zero. Again, this absolutely makes sense. You cannot go beyond that. Some input directions produce no output at all. So that, again, that makes sense, meaning that with redundancy, there are wasted input combinations. These can still create internal loads, heating, saturation, or structural stress. But again, internal loads or heating or saturation or structural stress are essentially wasted input combinations. Certain actuator force combinations cancel, resulting in no measurable effect. Consider this example: two motors driving the same shaft through gears. So we have two motors driving the same shaft through gears. Equal and opposite torques can cancel at the shaft output, but they still load the gearbox and generate heat, right? I have two inputs, but then these two inputs, and you do understand that we actually need just one, but then we have two inputs. And these two inputs, let's assume that we apply two motors driving the same shaft through gears. Equal and opposite torques can cancel at the shaft output. And you do understand that if I apply one Newton meters in clockwise direction through one motor, and then I apply a -1 Newton meter in the opposite direction, in counterclockwise direction, these two cancel each other, but still this would load the gearbox and generate heat. So essentially what happens is that direction, that input directions produce no output at all. Those two output inputs create no output, but then they create heat and load the gearbox. Let's assume we have three inputs and we have two outputs. Okay, so, and then we have this G as 2 by 3 matrix. So the three inputs make sense because we've got to have three inputs. This is essentially a simple model of redundant actuation. So we have three inputs, but then two outputs. Three actuators, but only two measured outputs. This plant maps a three-dimensional input space into a two-dimensional output space. Because output space is 2D at most, two independent effects can appear. So at least one input direction must be invisible in the outputs, because otherwise there needs to be a third output. But because we do have two outputs, then at least one input direction must be invisible in the outputs. So its singular value decomposition is U. And then we have this was, just to remind you, this matrix was our sigma matrix, and sigma has only two non-zero diagonal values because the rank is less than or equal to 2. The third diagonal is 0 and null direction exists. You can go back to the last lecture and take a look at how we define sigma and how that relates to U, and then the vector which describes the input and then the output. Only two singular values are non-zero, corresponding to the two independent output directions. Non-zero singular values, again, if you recall, we talked about sigma bar and sigma underscore, and we called the first one the maximum, or the worst case, the maximum amplification. And we defined the maximum amplification. We said that we assume a unit energy input. So if you go back to the previous slide, we had G, and then we talked about 2 norm of GD, assuming that D was 1, 0, a unit input. Of course, this has to be 1, 0, 0, because this is a 2 by 3 matrix, and that's a 3 by 1 matrix, which result in a 2 by 1 output. And then we can find the maximum sigma, or the maximum gain, or the maximum singular value, or our singular value, the worst case scenario. We can do the same thing, and assuming GD to norm, we can look for the minimum, and then based on that maximum and minimum, we can somehow create this sigma matrix. So the non-zero singular value, and obviously because the third input does not affect the output, because there is no way to map that input to output, we can already see why this third column would essentially be 0, 0. The smaller non-singular value is 1387, that sigma underscore, and the largest would be 7.354. Again, you can go back to your basic mathematics course, take a look at the 2 norm, and essentially quickly find that these two numbers, 7.354 and 1.387, worst case effective gain among directions that still get through is this 1387. So these two are the directions going through the system, because the third one does not actually go through the system. And this obviously that relates to other things like sensitivity to noise and control, sensitivity to noise. This is in only two. All right, so we have already talked about that. So this corresponds to weakest input direction that still produces non-zero output, 1387. The third input direction, input singular vector, is 0.588 minus 785,196, and G2V3 equals to 0. This direction lies in the null space of the plant. This vector is a recipe for a wasted actuator combination. So if you take a look at this, and G2 is exactly what the G you had 2 slides earlier, this is G2. Let's assume that this multiplies to pre-multiplies this V3, and of G2 V3, you can double check that results in 0. This direction essentially results in nothing, and this vector is an example for a wasted actuator combination. If you drive actuators in this ratio, outputs do not change. This direction lies in the null space of the plant. Null space directions create internal action but no measured effect. So let's look at engineering meaning. Inputs along with 3 produce no output. Input energy is wasted and makes site unmodeled dynamics. Controllers must avoid or suppress such directions. So even if, let me give you a real mechanical example about what we just talked about. Even if output doesn't change, internal states can change. For example, when actuators work, actuators may heat up. So actuator heating is an example of changing internal state. We might have a structural stress. We might have wear in drivetrain. We might have saturating amplifiers. So this saturation, this heat generation, these are examples of changing internal state. So we have more input than the number of outputs. This is a strong point to remember. Invisible, like something that does not change the output, does not mean harmless. It can actually harm the system because it can heat up the system, heat up internal actuators. Oh, I think I missed on the control implication is redundant actuators require careful coordination. So we need to plan allocation. We need to think about knowledge space projection. We need to think about optimization based control, and then we can think about all of this in terms of various applications. Let's look at this exercise. Consider a system with m inputs and exactly 1 outputs. There is exactly 1 non-singular value because we only have 1 output, and V identifies the most and least effective input combinations, and U reduces to a scalar phase or sign. Sign meaning that it does change the direction. So we have 1 output. The output direction is therefore fixed because we only have 1. The only real question is which combination of inputs moves that output most, because that's the only thing we are concerned about. With only 1 output, only the input direction matters. The output direction is fixed. Let me give you 1 example. For example, if you have 1 measured vibration amplitude, so 1 output, and then you have many shakers, so more than 1 input, then the question is which shaker combination maximizes vibration. If you only care about the vibration in the center of a plate, and then you have many shakers, then your question is which shaker combination maximizes vibration in the center of the plate. Okay, if I miss something, I try to remember and then go back to it later. Okay, now let's talk about a little bit about singular values for performance analysis. Let R omega be the reference vector and E omega corresponding error vector. You have already seen R reference and then E error in SISO. Oh, sorry, I missed any slide. Oh yeah, let me just go back and then restart. And so I missed 1 slide. I just remembered that there was a slide talking about SISO, then going to NMIMO. For its ISO system, the sensitivity, function determines tracking performance. So SISO at certain omega, we have E omega, in that omega, desired omega, as j omega r omega. In SISO, if norm absolute or magnitude of S is a small at low frequency, tracking is good, right? It's a small at low frequency. You should recall that from your first course in control, that low frequency disturbance rejection and tracking rely on a small sensitivity, and it makes sense. Low frequency disturbance rejection and tracking rely on a small sensitivity. The higher the sensitivity, the more problem we're going to have. S directly maps reference to disturbance inputs. So again, to the control errors. On the left hand side we had E, and then on the right hand side we have S, and then we have R. R was our reference, and then S was our sensitivity. All right. In S directly maps reference or disturbance inputs, same thing, appears in the same way in our equation, or disturbance inputs to the control error. Here S is the error transfer function. We can also develop an error transfer function. All right, a transfer function between reference and error. It tells you how much of the reference / disturbance leaks into error, right? Again, it tells you, this S tells you how much of the reference / disturbance leaks into error. Now let's go back to our MIMO generalization. Again, we have let R be the reference vector and E omega the corresponding error vector. Performance is measured using the vector 2 norm of E over 2 norm of R omega. And let me add one simple explanation about why norm appears. Like, why do we use 2 norm? Why norm in this case? When you have multiple outputs, just to remind you, because you should already be able to answer this question, why norm? When with multiple outputs, you need one number to summarize total error. But again, to remind you, as I said before, when we started talking about norms, I said that in real systems we use weighted norms. This weighted norms mainly because the units are different, and the output may not have the same to essentially be able to compute the norm. We need to compute the 2 norm of the input or output, essentially, because they have these various state variables or state parameters. To be able to add them together and essentially compute the 2 norm, we need to use a weighted average, and that weight essentially carries the sign for changing the unit, and then we can add them together. The 2 norm essentially captures the total error energy across across all outputs independent of coordinate choice. If I rotate the coordinate system of outputs, the 2 norm gives the same magnitude. I have just rotated the coordinate system, and you should recall that. If you don't recall that from, you should recall that from your many courses on basic mathematics or linear algebra, that if you rotate the coordinate system of outputs, the 2 norm gives the same magnitude. So that makes it a clean performance matrix, because the rotation does not essentially change the, sorry, I think I missed that slide. Yeah. The rotation does not change the magnitude. Since E equals SR, the gain depends on the direction of R. Using singular values, if you should recall that the sigma lowers underscore and sigma bar, or sigma upper score, I don't think we have something like called upper score, sigma lower score underscore, sorry, s j omega, and then sigma bar equal at s j omega. So what does it mean? What does this 2 norm e omega over 2 norm r omega? Again, e was the error and r was the reference vector and e was the error vector. And what does it mean? It means that same reference magnitude, different direction results in different error, right? Because the 2 norm captures both. What does it mean in engineering sense? It means that some command combinations are easy to track, others are hard, because those are weak directions. So we have strong directions that are easier to control or to track, and then we have directions, others are hard to track. These are weak directions. Engineering mean, what does it mean in engineering sense? It means that sigma bar gives the worst case amplification from reference to disturbance to error. Again, sigma bar s gives the worst case amplification from reference to disturbance from reference or disturbance to error. Yeah, let's go to the next slide. Maybe I can clarify a few things here. Performance requirement is we require a small error for all reference directions. Now this one completely makes sense. We require a small error for all reference directions, so it means that we are always looking for sigma bar s j omega, and s was the sensitivity at that j omega. Again, we're looking at the system at a certain time, so then we can talk about the frequency domain analysis of a MIMO system. Otherwise, if it wasn't certain j omega, then we would have problems. So we require a small error for all reference directions, so sigma bar s j omega is a small. So this is all directions. This is a key MIMO shift. You don't get to assume the reference is aligned with your favorite axis, right? Again, you don't know from the get-go that the reference, your reference vector, is aligned with your favorite axis. What if your reference is aligned with the weakest direction? What if the disturbance is aligned with the strongest direction? You don't get to assume from the get-go that these alignments are working in your interest. It doesn't work that way. In practice, reference and disturbance directions are uncertain. For example, aircraft gusts do not align neatly with roll only or pitch only. So again, these, and it makes sense, reference and disturbance directions are uncertain. So aircraft gusts, that sudden change in wind, you don't know ahead of time. You've got to assume that it could point in any direction. Direction meaning that it could point in any direction along any input. And let me also introduce a performance weight. So we have this performance weight, and we define it as 1 over WP, W subscript P, at j omega again, where everything we talk about is at j omega, is equal maximum allowable E omega 2 norm over R omega 2 norm. Let's think about it for a second. So this is just a definition. Obviously, by definition, we say that 1 over WPJ omega, the magnitude of 1 over WPJ omega, is equal to maximum allowable error over reference both 2 norms. It's just a definition. So a weight is a frequency dependent requirement. That's one thing. Low frequency demands small error. High frequency allows larger error. What does it mean? It means that weights encode engineering specifications such as tracking accuracy and disturbance rejections. Let me just give you an example. And again, it makes sense because let's assume this. So let's talk about rotation, for example. If your rotation is below 1 degrees per second or whatever, error must be less than 1%. But if it is 100 degrees per second, then we probably less care about that kind of error, because that error in that larger number essentially is dissolved, not dissolve or disappear, not disappear, it actually exists, but dissolved in that, considering that number. So we have a frequency domain performance condition. The weight, 1 over weight, is magnitude of weight, needs to be larger than sigma bar as j omega. If you multiply both sides by WPJ omega, we can say that WPJ as j omega is less than or equal to, sorry, it has to be less than 1. Well, what does it mean? If you recall, we talked about, again, sigma bar and sigma underscore. We talked about how they relate to the, what was that? It was the gain of the system. Again, sorry, I just feel like, again, I'm getting extremely tired. So how about this? Let's start next time. I'm gonna start at page 139 next time. All right, see you soon.